Look up at the night sky, and what do you see? A scattering of tiny, twinkling lights, stars so distant they seem no larger than pinpricks. But what if I told you that some of those stars are so unimaginably massive, they could swallow our entire solar system without a second thought? We're talking about cosmic titans, stars so colossal they defy logic, bending the very fabric of space around them. Take our sun, for example, a glowing sphere that could fit 1.3 million Earths inside it. Now picture a star so vast it makes the sun look like a speck of dust. That's the reality of hypergiants and supergiants, the universe's true giants, where the rules of physics twist into something almost unrecognizable. Imagine standing on a planet orbiting one of these monsters. The sky wouldn't just be lit, it would be dominated, overwhelmed by a searing wall of fire stretching from horizon to horizon. These stars don't just shine, they rage, burning through their fuel in mere millions of years, a blink in cosmic time compared to our sun's quiet 10 billion-year lifespan. And when they die, their final act is one of pure cataclysm, explosions so powerful they outshine entire galaxies for weeks, scattering the building blocks of life across the cosmos. These aren't just stars, they're the architects of the universe itself. But how do these behemoths form? What secrets do they hide in their blazing cores? And could one of them ever pose a threat to Earth? Over the next few minutes, we're diving deep into the heart of these celestial giants, uncovering 30 facts that will change the way you see the night sky forever. From stars so bright they'd cast shadows at night from thousands of light years away, to one so dense a single teaspoon of their material would weigh more than a mountain, this is a journey to the edge of what's possible. So buckle up, the universe is about to show you just how small we really are and how utterly astonishing its true scale can be. Even among the universe's most colossal stars, one stands out as the reigning king of sheer size, VY Scuti. Picture this: if you swapped our sun with this monstrous red hypergiant, its outer layers would stretch beyond the orbit of Saturn, swallowing Mercury, Venus, Earth, Mars, Jupiter, and even the rings of Saturn in a single fiery embrace. Just the thought of standing on a planet within that star's shadow is mind-bending. Instead of a sun in the sky, you'd see a swirling ocean of plasma stretching across almost the entire horizon. But VY Scuti's enormity isn't just about physical scale. This star burns with a luminosity nearly 300,000 times brighter than our sun, a searing beacon visible from thousands of light years away. And yet, despite its brilliance, it's classified as a red hypergiant, cooler than many younger, bluer stars but unimaginably vast, like a cosmic balloon stretched to its limit. Stars like this don't just defy expectations, they rewrite the rules. What makes VY Scuti and other hypergiants so volatile is their own sheer mass. They're not just big, they're unstable, shedding colossal amounts of material into space in violent eruptions. Imagine a star so massive that it's constantly tearing itself apart, its outer layers drifting away in vast clouds of gas and dust. And here's the haunting part: these giants live fast and die young. While our sun will shine steadily for billions of years, VY Scuti is racing toward its fate, destined to end in one of the most spectacular explosions the universe can produce. So the next time you gaze up at the stars, remember, somewhere out there, VY Scuti looms like a silent titan, a reminder of just how small and how extraordinary our corner of the cosmos truly is. While VY Scuti holds the title for sheer immensity, its neighbor VY Canis Majoris reveals an even more dramatic truth: hypergiants aren't just massive, they're cosmic pressure cookers on the verge of bursting. These stars don't gently glow, they erupt, ejecting enough material in a single year to build an entire solar system. Picture a hurricane of stellar wind so powerful it could strip a planet's atmosphere clean away in seconds. That's the everyday reality for these unstable giants. What makes them so volatile? It all comes down to gravity's losing battle against radiation. Deep in their cores, hypergiants fuse elements at a frenzied pace, generating enough outward pressure to counteract their own crushing weight. But as they age, that balance tips. The star's outer layers, stretched impossibly thin by its enormous size, become gravitationally unbound. The result? Massive eruptions where the star literally blows off chunks of itself, enough material to form multiple Jupiters in what astronomers call superwinds. This isn't some slow, steady leak. Observations of VY Canis Majoris reveal titanic plasma arcs, vast loops of star stuff flung outward at speeds exceeding 300,000 miles per hour. To put that in perspective, if Earth orbited within this star's vicinity, these eruptions would bathe our planet in enough radiation to sterilize its surface in moments. And here's the cruel irony: the very process that makes hypergiants so spectacular also dooms them. While our sun conserves its fuel like a careful saver, these stars burn through their hydrogen reserves in just a few million years, less than 0.1% of the sun's lifespan. Their furious energy output comes at a cost, like a billionaire spending their entire fortune in a single night. But this recklessness serves a purpose. The material these stars shed doesn't just vanish, it enriches the cosmos with heavy elements, seeding future generations of stars and planets. Every iron atom in your blood, every calcium molecule in your bones was forged in such stellar furnaces long ago. Hypergiants may live fast and die young, but in their spectacular demise, they give birth to the building blocks of life itself. VY Canis Majoris isn't just a dying star, it's a cosmic time bomb ticking toward one of the most violent explosions in the universe. Right now, this hypergiant is shedding mass at an almost unimaginable rate, losing the equivalent of Earth's entire mass every single day. To put that into perspective, if our sun were to lose material at the same rate, it would vanish completely in just 100,000 years. But VY Canis Majoris, it's been doing this for centuries, shrouding itself in a vast nebula of its own ejected material, like a phoenix wrapping itself in flames before rebirth. What makes this star truly extraordinary isn't just its size, though it's large enough to swallow Jupiter's orbit whole, but its instability. Unlike steadier stars, VY Canis Majoris pulses and convulses, its outer layers sloshing like water in a giant's bowl. Some astronomers compare it to Betelgeuse, the red supergiant in Orion's shoulder, but even Betelgeuse seems tame by comparison. While Betelgeuse's dimming events spark speculation about an impending supernova, VY Canis Majoris is already in the advanced stages of stellar decay, its core racing toward collapse. And when that collapse comes, the explosion will be unlike anything in recorded history. A typical supernova outshines its entire host galaxy for weeks, but hypergiants like this one could produce something even more extreme: a hypernova, paired with a devastating gamma-ray burst. The energy released in just a few seconds would eclipse the sun's lifetime output. If such an event happened within a few thousand light-years of Earth, the radiation alone could strip away our ozone layer, triggering mass extinctions. Yet for all its destructive potential, VY Canis Majoris is also a cosmic alchemist. The elements forged in its core, carbon, oxygen, even gold, will be scattered across the galaxy, destined to one day become part of new stars, planets, or even life. In its death, this star will give birth to the building blocks of future worlds. That's the paradox of these hypergiants. They're both destroyers and creators, ending their lives in chaos while seeding the universe with the very ingredients of existence. Hidden behind thick cosmic dust clouds in the constellation Ara lies a star so enormous it challenges our very understanding of stellar physics, Westerlund 126. This red hypergiant, shrouded in mystery, is so distant and obscured that astronomers still debate its true size. Some estimates suggest if placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, making even VY Scuti seem modest by comparison. Yet unlike its better-known cousins, Westerlund 126 lurks in the shadows, its light dimmed by interstellar dust like a lighthouse smothered by fog. Studying this cosmic titan is like trying to decipher a whisper in a hurricane. Located 19,000 light-years away within the dense star cluster Westerlund 1, it's surrounded by swirling debris and younger, hotter stars whose glare drowns out its signal. Infrared telescopes have pierced some of that veil, revealing a star not just massive but strangely variable, pulsing unpredictably as it teeters on the edge of stability. One year it might shine 50,000 times brighter than the sun. The next it dims to near invisibility. This isn't just a star, it's a celestial enigma defying categorization. What truly sets Westerlund 126 apart is its extreme environment. Nestled in a cluster of supergiants, it's bombarded by radiation from neighboring stars, which may explain its erratic behavior. Some theorists suggest it's not just a hypergiant but a failed supernova, a star so massive it should have exploded long ago, yet somehow keeps clinging to existence. Its outer layers are so tenuous they blur the line between star and nebula, with vast plumes of gas stretching billions of miles into space. The challenges of observing Westerlund 126 reveal a humbling truth. Even our most advanced telescopes struggle to comprehend the universe's most extreme objects. Every new data point brings more questions. Is it truly the largest star we've discovered, or does dust distort our measurements? Is its flickering light a prelude to collapse, or just another phase in its turbulent life? For now, this monster remains a puzzle, a reminder that the cosmos still holds secrets too vast for even our boldest imaginations to grasp. These stellar behemoths are far more than just spectacular light shows. They're the universe's ultimate recyclers, transforming their violent deaths into the building blocks of future galaxies. When a hypergiant star exhausts its nuclear fuel, the resulting supernova explosion scatters newly forged heavy elements across vast interstellar distances at nearly 10% the speed of light. A single dying star can enrich thousands of light-years of space with elements like carbon, oxygen, silicon, and iron, the very materials that eventually coalesce into new stars, planets, and even life itself. This cosmic recycling process begins in the star's final moments. As fusion reactions in the core start creating nickel and iron, the star's gravity suddenly overwhelms the outward pressure. The core collapses in milliseconds so rapidly that shockwaves rip through the outer layers, triggering an explosion visible across the universe. The energy released during this detonation is staggering, more than the sun will emit in its entire 10-billion-year lifetime, concentrated into a few Earth-shaking seconds. Temperatures reach billions of degrees hot enough to forge gold, uranium, and other heavy elements through rapid neutron capture. The aftermath resembles a cosmic smelting furnace. Expanding shock waves from the supernova compress nearby gas clouds, triggering new star formation while simultaneously peppering them with heavy elements. Observations of young star clusters show this pattern clearly. Generations of stars born from the ashes of their massive predecessors, each new batch richer in metals than the last. Our own solar system likely formed from a nebula contaminated by at least one ancient hypergiant's death throes, which explains why Earth contains elements like calcium for our bones and silicon for our rocks. What's truly remarkable is the scale of this enrichment. Galactic surveys reveal chemical gradients, regions where supernova remnants have created bubbles of element-rich gas that eventually collapse into new stellar nurseries. The Orion Nebula, currently birthing hundreds of new stars, shows this process in action, with spectral lines revealing abundant oxygen, carbon, and nitrogen, all gifts from long-dead massive stars. Even more dramatic are superbubbles, structures hundreds of light-years wide created by multiple hypergiant explosions, which reshape entire galaxies by triggering waves of star formation. Without these massive stars acting as galactic alchemists, the universe would be a far poorer place, literally. Early in cosmic history, only hydrogen and helium existed. It took generations of hypergiants living and dying to create the diversity of elements needed for rocky planets, organic molecules, and ultimately, life. Every time you take a breath, you're inhaling oxygen atoms forged in some ancient star's cataclysmic demise. The gold in your jewelry that was likely created during the violent collision of neutron stars triggered by a hypergiant's collapse. These stellar titans may be rare and short-lived, but their legacy echoes through every atom in our bodies and every world in our galaxy. Here's something that might shock you. The universe's most massive stars live lives that are incredibly short and unimaginably intense. While our dependable sun will shine steadily for about 10 billion years, a hypergiant star like Eta Carini races through its entire existence in just 2 or 3 million years. That's like comparing a mayfly's single day to a human lifetime. These cosmic giants burn their nuclear fuel at a breakneck pace, fusing elements so rapidly that their cores become furnaces of unimaginable pressure and temperature. The reason comes down to simple physics. The bigger the star, the more gravity crushes its core, forcing atoms to collide with terrifying energy. A star 10 times more massive than the Sun doesn't just burn 10 times brighter. Its luminosity skyrockets to thousands of times greater, like swapping a candle for a flamethrower. This reckless consumption comes at a cost. Where smaller stars conserve fuel for eons, hypergiants exhaust theirs in a cosmic blink, their brilliance a desperate scramble against their own crushing weight. And when they finally run out of fuel, the collapse is catastrophic. Unlike the Sun, which will fade peacefully into a white dwarf, these titanic stars die in some of the most violent explosions, known supernovas so powerful they briefly outshine entire galaxies. Some may even collapse into black holes, their cores imploding under gravity's unstoppable grip. The heavier the star, the more dramatic its demise, yet this very brevity is what makes them vital. In their short, fiery lives, they forge elements no smaller star could ever produce: oxygen for our lungs, calcium for our bones, iron for our blood. Then, in death, they scatter these materials across the cosmos like celestial gardeners, seeding the universe with the ingredients for new stars, planets, and life itself. Their existence may be fleeting, but without their violent generosity, the universe as we know it simply wouldn't exist. If you think all hypergiant stars are equally blistering infernos, think again. These celestial titans span an astonishing range of temperatures, from cool 3,000-degree surfaces on red hypergiants like VY Canis Majoris to blue supergiants like Eta Carini blazing at over 40,000 degrees, hotter than a welding torch's core flame. That's not just a difference in heat, it's a fundamental shift in how these stars live, burn, and ultimately die. Take the red hypergiants first. These colossal stars, often over 1,000 times the Sun's radius, appear cooler because their energy is spread across such vast surfaces. Picture a bonfire versus a blowtorch. The bonfire's heat feels gentler because it's dispersed, but its total energy could melt steel. Similarly, a red hypergiant's relatively cool surface belies the chaos within. Their outer layers puff out like cosmic smoke, dimming their glow while hiding seething interiors where fusion reactions rage unchecked. Now contrast that with a blue supergiant like Eta Carini. Here, radiation isn't just intense, it's apocalyptic. The star's ultraviolet output is so extreme it ionizes surrounding gas, carving nebulas with its sheer energy. At 40,000 degrees, its surface would vaporize any known material instantly, while stellar winds scream outward at millions of miles per hour. These aren't just stars, they're cosmic blowtorches burning so fiercely they can barely hold themselves together. The secret behind this temperature divide lies in their mass and age. Red hypergiants are often older, having expanded as their cores fused heavier elements, while blue supergiants are younger and more compact, their energy concentrated into smaller, fiercer frames. But there's a twist. Some stars flip between these states. Eta Canis itself may have been a red supergiant before shedding layers and heating up again, proving these giants are as unpredictable as they are immense. What does this mean for the cosmos? Temperature dictates a hypergiant's influence on its surroundings. Cooler red giants enrich space with dust that blocks light and nurtures molecule formation, while blue supergiants flood their neighborhoods with radiation that shreds apart fledgling planets. Both are vital. One builds, the other sculpts, and together they shape galaxies in ways we're only beginning to understand. In the mid-19th century, astronomers around the world witnessed something unprecedented. A star normally invisible to the naked eye suddenly flaring into the second brightest object in the night sky, outshone only by Sirius. This was Eta Canis, a hypergiant star already notorious for its instability, staging what we now call the Great Eruption. For over a decade, it burned with an intensity that defied explanation, ejecting enough material to form multiple stars before mysteriously fading again. Today, we see the aftermath of vast, hourglass-shaped nebula glowing with the echoes of that violent outburst, a cosmic scar stretching trillions of miles into space. What made this eruption so extraordinary wasn't just its scale, but its peculiar shape. Unlike a typical supernova's spherical explosion, Eta Canis expelled matter in two opposing jets, creating the distinctive bipolar nebula we observe now. Some scientists believe this reveals a hidden companion star, a gravitational accomplice whose pull may have funneled the outburst into those focused streams. Others theorize the star's own rotation, spinning at breakneck speeds, could have flattened the explosion like a cosmic squashed balloon. Either way, the result is a celestial artwork, illuminated by shockwaves where ejected gas collides with older debris at speeds approaching 500,000 miles per hour. The most chilling realization, the Great Eruption wasn't the star's death throes, it was merely a warning shot. Eta Canis is still here, more unstable than ever, its core teetering on the edge of collapse. When it finally does explode, the event could dwarf even the Great Eruption, potentially unleashing a gamma-ray burst, one of the universe's most destructive phenomena. For context, a typical supernova releases as much energy in months as the Sun will in its entire lifetime. A hypergiant like Eta Canis, it could match that output in seconds, flooding nearby space with radiation capable of stripping atmospheres from planets light years away. Yet within this cataclysm lies a paradox. The same forces that make Eta Canis so dangerous also make it indispensable. The heavy elements forged in its core, oxygen, neon, magnesium, will eventually seed new solar systems. Its eruptions, violent as they are, compress nearby gas clouds, triggering the birth of future stars. This is the duality of the cosmos, destruction and creation intertwined, with hypergiants like Eta Canis playing both roles simultaneously. So while we watch and wait for its inevitable demise, remember this star's final act may one day pave the way for new worlds, and perhaps even new life in the distant future. Luminous blue variables like Eta Canis are the universe's ultimate wildcards, stars so unstable they rewrite the rulebook of stellar physics with every eruption. These celestial rebels don't follow the quiet, predictable life cycles of normal stars. Instead, they convulse in violent outbursts, throwing off entire solar systems worth of material in fits of cosmic temper tantrums. But what drives this extreme behavior? The answer lies in a delicate and doomed balancing act between two unstoppable forces. Deep within a luminous blue variable, radiation pressure from the star's core fights a constant war against gravity's crushing grip. Normally, these forces stay in equilibrium, but when the star grows too massive, often 150 times heavier than our Sun, the balance shatters. The radiation becomes so intense it literally pushes the star's outer layers into space, like a hurricane tearing roofs off houses. This creates periods of extreme mass loss where the star can eject 10 Earth masses of material every year, shrouding itself in thick clouds of glowing gas. The strangest part, these outbursts aren't random. They occur when the star's outer layers expand and cool just enough for electrons to recombine with atoms, making the gas suddenly more opaque. Trapped radiation builds pressure until, like a steam kettle with no release valve, the star violently expels its outer shells. VY Canis' great eruption likely followed this pattern when it hurled out 30 suns worth of material in just 20 years, creating the homunculus nebula we see today. Yet even this explanation leaves mysteries. Why do some outbursts leave bipolar nebulae while others create chaotic debris fields? Why do these stars sometimes quiet down for centuries before erupting again? Some theorists suggest hidden companion stars might trigger the eruptions, their gravitational tugs destabilizing the hypergiants' outer layers. Others propose that deep magnetic fields, twisted like cosmic rubber bands, suddenly snap and release pent-up energy. What's undeniable is how these events transform our understanding of stellar life cycles. Textbook models can't fully explain why luminous blue variables oscillate between calm and chaos, or why some survive multiple eruptions instead of collapsing. Each new observation, like Hubble's recent images showing vast, fast-moving knots in VY Canis Nebula, adds another puzzle piece. These stars remind us that the universe's most spectacular phenomena often defy simple categorization, forcing scientists to rethink decades of assumptions about how stars live, die, and reshape the cosmos around them. Imagine a star so massive it dwarfs everything in its galaxy, yet it could never exist today. The universe's earliest stars, born from pristine hydrogen and helium, had a staggering advantage. They grew larger than anything we see now because they lacked one critical ingredient: metals. In astronomy, metals mean any element heavier than helium, and their absence in the early cosmos allowed stars to balloon to sizes we can barely comprehend. This cosmic recipe for gigantism comes down to how metals cool star-forming clouds. In modern nebulae, elements like carbon and oxygen act as cosmic refrigerants, radiating heat away and letting gas clump into denser pockets. That might sound helpful, but there's a catch. These dense fragments lead to many smaller stars rather than a few behemoths. Contrast that with the primordial universe where gas couldn't cool efficiently, remaining hot and diffuse. Without metals to siphon away heat, these clouds collapsed into single, monstrous stars instead of breaking apart, some possibly reaching 1,000 solar masses or more. The evidence lies in distant quasars whose light captured the chemical fingerprints of these first-generation stars, called Population 3. Their supernova enriched the cosmos with its first heavy elements, altering star formation forever. Today, even the most metal-poor regions of space still contain traces of these recycled materials, enough to cap star sizes at a mere few hundred solar masses. But here's the twist: metallicity isn't just about size. It sculpts a star's entire life. Metal-rich stars like our Sun have thicker outer layers that absorb radiation, leading to convective surfaces and longer lives. Metal-poor stars, by contrast, burn hotter and clearer, their innards exposed like cosmic X-rays. Had the first hypergiants survived, their skies would have blazed with ultraviolet light, sterilizing any fledgling planets. This delicate interplay between chemistry and gravity means the universe's true giants may be forever lost to time, their era ending as soon as it began. Yet their legacy lives on, in the metals they forged, the galaxies they seeded, and the cosmic rules they rewrote with their brief, brilliant lives. Deep in the heart of the Tarantula Nebula, a swirling stellar nursery 160,000 light-years away, lurks a star so massive it pushes the limits of physics itself. Meet R13601, the heavyweight champion of known stars, tipping the scales at over 250 times the mass of our Sun. To grasp just how staggering that is, picture this. If R13601 replaced our Sun, its gravitational pull would yank Earth's orbit inward so violently that a single year would last just 3 weeks. What makes this star truly baffling isn't just its size, but its very existence. For decades, astronomers believed stars couldn't exceed 150 solar masses, a theoretical limit called the Eddington limit, where radiation pressure should blow apart anything larger. Yet R136A1 laughs in the face of that rule, burning with the brilliance of nearly 9 million suns. How did it grow so unimaginably huge? The leading theory points to its chaotic birthplace. The Tarantula Nebula is no ordinary stellar nursery. It's a hyperactive factory of star formation, where colliding gas clouds create perfect conditions for monsters to emerge. Here, gravity works overtime, pulling together vast amounts of material before radiation from newborn stars can dissipate it. Some scientists suggest R136A1 might have formed from the merger of 2 massive protostars, their violent embrace birthing a single, unmatched titan. Others propose it grew by cannibalizing smaller neighbors, stealing their mass like a cosmic kingpin. But R136A1's reign won't last. Stars this massive live life in the fast lane, burning through their fuel in just 2 million years, a cosmic heartbeat compared to our sun's 10 billion-year lifespan. Already, its stellar winds blast outward at nearly 6 million miles per hour, stripping away 50 Earth masses of material every year. This isn't just a star, it's a runaway train, hurtling toward an inevitable collapse that might leave behind one of the universe's most enigmatic remnants, a black hole with the mass of a small galaxy. Yet for all its ferocity, R136A1 serves a grander purpose. Its ultraviolet radiation sculpts the surrounding nebula, ionizing gas clouds and triggering new star formation even as it tears itself apart. Every atom it ejects will one day become part of future worlds, perpetuating a cycle as old as the cosmos itself. The Eddington limit stands as one of astrophysics' most fundamental rules, a cosmic speed bump preventing stars from growing indefinitely. Named after British astronomer Arthur Eddington, this principle states that every star exists in a precarious balance. On one side, gravity relentlessly crushes inward, compressing the star's core. On the other, radiation pressure from nuclear fusion pushes outward, resisting collapse. The Eddington limit marks the tipping point where these forces become unbalanced, where a star's radiation grows so intense it overcomes gravity's grip, blasting away its outer layers like a hurricane tearing apart a sandcastle. For decades, astronomers believed this limit capped star sizes at around 150 solar masses. Beyond that, conventional wisdom said radiation pressure would strip a star bare before it could grow larger. Yet R136A1, a behemoth weighing 250 solar masses, shatters that assumption. It's the equivalent of discovering a skyscraper standing tall in a zone where physics insisted only single-story homes could exist. How does this cosmic rebel defy the rules? The answer lies in its extreme environment. Nestled in the dense, metal-rich Tarantula Nebula, R136A1 may owe its existence to a perfect storm of conditions. Unlike primordial stars that formed in pristine gas clouds, this hypergiant grew up surrounded by heavier elements that helped trap radiation, allowing gravity to pile on more mass before outward pressure could intervene. Some simulations even suggest it formed through violent stellar mergers, multiple massive stars colliding like cosmic freight trains, their combined mass breaching the theoretical ceiling. But the real surprise isn't just that R136A1 exists, it's how it survives. At 9 million times the sun's luminosity, its radiation pressure should be apocalyptic. Yet observations reveal a paradoxical phenomenon. Despite its unimaginable brightness, the star remains shrouded in thick stellar winds, a self-generated veil of gas and dust that absorbs and re-radiates energy, effectively cheating the Eddington limit by spreading the pressure over a larger area. It's like a pressure valve bleeding off excess steam, enabling the star to retain its gargantuan bulk. This discovery forces scientists to reconsider stellar physics itself. Could the Eddington limit be more flexible than we thought? Are there other mechanisms like rapid rotation or magnetic fields that let stars bypass these constraints? Every new observation of R136A1 peels back another layer, revealing a universe where even our most cherished rules have exceptions hiding in plain sight. And that's the true lesson here. Astrophysics isn't a set of rigid laws, but an evolving dialogue between theory and the cosmos' endless creativity. In the cosmic dance of binary star systems, some partnerships take a deadly turn, where one star becomes a stellar vampire, draining its companion's lifeblood. Few examples are as dramatic as HD 5980, a binary hypergiant system where two massive stars orbit so closely that one actively strips material from the other, like a celestial parasite feeding on its host. The stolen gas spirals inward, forming a searing accretion disk hotter than the surface of most stars, a visible testament to this ruthless cosmic theft. The mechanics of this vampirism reveal the brutal reality of gravitational dominance. When two stars orbit near each other, the more massive one exerts a stronger gravitational pull, warping its companion's shape into a teardrop. At a critical point, material from the victim star's outer layers crosses the boundary, known as the Roche lobe, and falls irrevocably into the vampire's grasp. This stolen hydrogen fuels the aggressor, making it grow even larger while the donor star withers, its structure destabilized by the loss. HD 5980 takes this violence to extremes. Located in the Small Magellanic Cloud, this system contains two luminous blue variables, stars already prone to instability, locked in a 4.5-day orbital embrace. Observations show eruptions where the mass-gaining star ejects stolen material in spectacular outbursts, suggesting this vampirism isn't always smooth. Like a glutton overeating, the vampire star sometimes regurgitates what it's consumed, creating vast nebulae around the pair. But here's the twist: the victim might have the last laugh. In some cases, the donor star evolves faster due to mass loss, collapsing into a neutron star or black hole before its companion. Suddenly, the predator becomes prey, as the newly formed compact object starts siphoning material back from its former tormentor. This reversal of fortune illustrates the universe's dark humor: stellar relationships where dominance is always temporary, and the hunter can so easily become the hunted. The aftermath of this cosmic heist reshapes both stars' fates. The thief, bloated with stolen fuel, burns hotter and brighter, racing toward an early supernova. The donor, stripped to its core, may transform into a Wolf-Rayet star, a rare hydrogen-depleted object that sheds its remaining mass in furious stellar winds. Their entwined destinies show how binary systems are laboratories for extremes, where gravity and radiation conspire to create scenarios no single star could experience alone. What makes these systems so fascinating isn't just their violence, but their role in galactic chemistry. The turbulent interactions in binaries like HD 5980 eject heavy elements at incredible speeds, enriching interstellar space with material that becomes the building blocks of planets and life. Even in their predatory dance, these stars serve a grander purpose, proving that in the cosmos, destruction and creation are often two sides of the same coin. The life and death of the universe's most massive stars isn't just a spectacle, it's a high-stakes cosmic experiment where the laws of physics face their ultimate test. When these titanic objects reach the end of their short, violent lives, their fate hinges on a razor-thin balance between two unimaginably powerful forces: gravity's relentless inward pull versus the explosive energy of nuclear fusion. The outcome of this battle determines whether these stars will vanish in the most energetic explosions known to science or leave behind space-time's most enigmatic objects. Stars between around 8 and 40 solar masses typically end their lives as neutron stars, incredibly dense remnants where a sun's worth of mass gets crushed into a sphere no wider than Manhattan. But for the true hypergiants, those weighing in at over 40 solar masses, the story takes a darker turn. Their cores become so massive that even neutron degeneracy pressure, the quantum force that keeps neutron stars from collapsing further, can't withstand gravity's pull. The core implodes past the point of no return, forming a black hole so dense that not even light can escape its grip. Yet there's an even more dramatic fate awaiting the most extreme hypergiant stars topping 130 solar masses. These rare monsters face a bizarre phenomenon called pair instability, where conditions in their cores become so extreme that gamma-ray photons spontaneously transform into matter electron-positron pairs. This process saps energy from the star's core, removing the pressure that was holding gravity at bay. The result, a runaway collapse followed by a thermonuclear detonation so violent that it obliterates the star completely. No black hole, no neutron star, just an expanding cloud of stellar debris. The threshold between these fates is terrifyingly precise. Stars between 130 and 250 solar masses may experience partial pair instability events, where multiple pulsations strip their outer layers before final collapse. But cross that upper limit like the suspected 260 solar mass behemoth that created the enormous SN 2007 BI supernova, and the star detonates with such force that it can briefly outshine its entire host galaxy. Astronomers call these explosions hypernova, and they're among the most energetic events since the Big Bang itself. What makes these deaths particularly fascinating is how they shape the cosmos. Black holes formed from collapsing hypergiants become gravitational anchors, some eventually growing into the supermassive black holes that lurk at galaxy centers. Pair instability supernova, meanwhile, scatter vast amounts of heavy elements across interstellar space, enriching future generations of stars with the building blocks for planets and life. Yet mysteries remain. Recent observations of gravitational waves suggest some black holes form with masses that challenge our understanding of stellar evolution, hinting at unknown processes in these final moments. Every hypergiant death we witness adds another piece to this cosmic puzzle, revealing how the universe's largest stars forge both its darkest objects and its brightest explosions. When nature pushes matter to its absolute limits, even stars can't hold themselves together. Pair instability supernovas represent the most catastrophic stellar deaths imaginable, explosions so powerful they vaporize entire stars down to their last atom, leaving no black hole or neutron star behind. These cosmic detonations occur exclusively in hypergiant stars between 130 and 250 solar masses, where the core becomes a runaway nuclear reactor with no failsafe. The physics behind these explosions is as bizarre as it is violent. Under normal circumstances, a star's core resists gravity's crush through radiation pressure, photons generated by fusion literally pushing outward. But in the hearts of these ultra-massive stars, temperatures soar above 1 billion degrees, making gamma-ray photons so energetic they spontaneously transform into matter electron-positron pairs. This conversion acts like a cosmic power outage. Suddenly, the radiation propping up the star vanishes, like yanking the supports from a collapsing bridge. Gravity wins instantly. The core implodes in milliseconds, heating further until oxygen and silicon begin fusing uncontrollably. What happens next defies belief. The entire star detonates like a thermonuclear bomb the size of our solar system. Unlike ordinary supernovas that leave behind dense remnants, pair instability blasts obliterate every trace, converting the star's mass into pure energy and scattering heavy elements across thousands of light years. The light from a single event can briefly rival the output of an entire galaxy, shining with the intensity of 20 billion suns. The rarity of these explosions reveals something profound about our universe. We've only observed a handful of candidates like SN 2007 Bi, a supernova 6 times brighter than any other recorded. Its light curve matched predictions perfectly. A slow fade as ejected nickel 56 decayed, proving the star had been completely vaporized. Other potential cases like SN 2002 GHY show similar fingerprints, no compact remnant, just an expanding shell of stellar debris rich with silicon and iron. These explosions serve as cosmic regulators. By preventing the formation of mid-sized black holes from hypergiant stars, pair instability supernovas may have shaped the early universe's growth, limiting how quickly black holes could grow. Yet paradoxically, their destructive fury also seeded galaxies with the heavy elements needed for rocky planets and life. Every iron atom in Earth's core, every calcium molecule in your bones, likely originated in such an apocalyptic detonation billions of years ago. The legacy of these stars lives on not in corpses, but in the echoes of their annihilation, reminders that even the mightiest objects in existence are fleeting, their deaths rewriting the rules of cosmic chemistry with every universe-shattering blast. Astronomers face a cosmic puzzle when counting hypergiants. These titanic stars should be far more common than what we actually observe. Theory predicts that for every 1,000 ordinary stars, there should be several hypergiants blazing across the galaxy. Yet scanning the heavens reveals barely a handful. So where are all the missing behemoths? The answer lies in a perfect storm of cosmic rarity, fleeting lifespans, and the universe's own veils of dust and gas. First, consider the brutal brevity of a hypergiant's existence. These stars don't just burn bright, they burn out fast, with lifetimes measured in mere millions of years compared to the sun's 10 billion. That's like comparing a fireworks spark to a candle's steady glow. By cosmic standards, hypergiants are here one celestial moment and gone the next, leaving little time for astronomers to catch them in their prime. Compounding the issue, their most dramatic phases, like the violent eruptions of luminous blue variables, are even shorter, sometimes lasting just decades before the star collapses or transforms. Then there's the challenge of dust. Hypergiants are messy eaters, shedding colossal amounts of material in stellar winds thick enough to shroud entire solar systems. This self-made debris acts like a cosmic smokescreen, dimming the star's light across visible wavelengths. Some, like Westerlund 126, lurk behind such dense veils that only infrared telescopes can pierce through. Others, like Rho Cassiopeiae, occasionally vanish from view entirely as ejected gas condenses into dust clouds. It's a cruel irony. The same processes that make hypergiants so fascinating also hide them from our view. But perhaps the most surprising factor is location. Hypergiants avoid galactic suburbs, preferring crowded stellar nurseries like the Tarantula Nebula, where thick dust lanes and overlapping star clusters make observation a nightmare. Even in these active regions, their light competes with thousands of neighbors, blending into the background like a single shout in a roaring stadium. Add to that the vast distances involved. Many hypergiants sit tens of thousands of light years away, and the challenge becomes clear. We're trying to study faint candles through a fog bank while standing miles away. Yet new technologies are peeling back these obscuring layers. Radio telescopes now trace hypergiant winds molecule by molecule, while space observatories like JWST detect their heat signatures through dust. Each discovery hints at a hidden population, suggesting these stars aren't as rare as we once thought, just masterful cosmic hide-and-seek players. The next breakthrough might reveal entire families of hypergiants lurking in plain sight, waiting for the right tools to uncover their secrets. Until then, their absence reminds us that the universe's grandest spectacles often unfold behind the darkest curtains. Near the chaotic heart of our galaxy, where stars orbit at dizzying speeds around a supermassive black hole, one hypergiant stands out not just for its brilliance but for its sheer audacity. The Pistol Star, a blue hypergiant lurking 25,000 light-years away, burns with the intensity of 10 million suns, so luminous it would outshine the full moon if placed at the distance of Alpha Centauri. Its name comes from the eerie, pistol-shaped nebula surrounding it, a vast cloud of gas and dust stretched into that peculiar form by the star's relentless stellar winds, which blast outward at nearly 100 billion times the speed of the solar wind. What makes this star truly extraordinary isn't just its energy output, but its origin story. Unlike most hypergiants nestled in dense star clusters, the Pistol Star appears to be a cosmic loner, drifting through the galaxy's central region like a rogue titan. Some astronomers believe it was violently ejected from its birthplace, perhaps flung outward by gravitational interactions with other massive stars, or even the supermassive black hole Sagittarius, a star. If true, this stellar fugitive now barrels through space at staggering speeds, its radiation carving a path through interstellar gas like a ship plowing through cosmic waves. The Pistol Star's luminosity comes at a cost. It's shedding mass at an almost incomprehensible rate, roughly 10 Earth masses every year, through winds so intense they've blown away much of the star's outer layers. This self-destructive behavior means the star has already lost 50 times the Sun's mass in just a few million years. The debris forms that iconic nebula, glowing not from starlight but from the collisions between ejected material and interstellar gas, a celestial light show spanning 4 light-years across. Yet for all its ferocity, the Pistol Star is living on borrowed time. Blue hypergiants like this exist in a precarious state, perpetually on the edge of instability. Current estimates suggest it began life with 200 times the Sun's mass, pushing the theoretical limits for star formation, but has since slimmed down dramatically. Its fate hangs in the balance. Will it collapse directly into a black hole, or explode in a supernova so bright it'd briefly outshine the galactic core? One thing's certain: the Pistol Star serves as a reminder that even in the crowded galactic center, individuality shines through. While most stars follow predictable orbits, this rebellious giant charts its own course, leaving behind a glowing testament to its power. Every atom it ejects enriches the galaxy's central bulge, contributing to the chemical stew that might one day form new stars, or even planets capable of bearing life. Hidden behind curtains of cosmic dust, hypergiant stars like the Pistol Star have long kept their secrets until now. The James Webb Space Telescope, with its unprecedented infrared vision, is peeling back these veils one layer at a time, revealing details about these stellar titans that were previously impossible to see. While optical telescopes struggle to penetrate the thick clouds of gas and dust surrounding hypergiants, JWST instruments cut straight through, capturing heat signatures and chemical fingerprints invisible to other observatories. Take the Pistol Star. JWST recent images show intricate structures in its nebula that were completely obscured before. Swirling filaments of ionized gas, vast plumes of ejected material, even shockwaves where stellar winds collide with older debris, all now visible in stunning detail. But the telescope isn't just providing better pictures, it's rewriting our understanding of how these stars lose mass. Spectroscopic data reveals unexpected elements like titanium oxide and silicate grains in the Pistol Star's winds, suggesting hypergiants may forge and distribute complex molecules in ways no model predicted. Perhaps the biggest breakthrough is timing. Hypergiants evolve so quickly that even a decade of observations feels like a snapshot, but JWST precision lets astronomers track changes in real time. The Pistol Star, for instance, shows unusual fluctuations in its infrared brightness, hinting at instabilities deep within its core that could signal an impending eruption or collapse. Similar observations of other hypergiants like Eta Carini and VY Canis Majoris reveal asymmetrical mass ejections, proof that their deaths won't be the symmetrical explosions we once assumed. The telescope's greatest contribution might be solving the missing hypergiant mystery. By scanning star-forming regions in infrared, JWST has uncovered dozens of massive stars previously hidden in dusty cocoons, suggesting these giants are more common than we thought, just exceptionally good at hiding. Some could even be failed supernova, stars massive enough to collapse directly into black holes without the fireworks we'd expect. Every new dataset feels like lifting another corner of a cosmic tapestry, one where hypergiants are not just oddities but key players in galactic evolution. Their winds, eruptions, and death shape entire nebulae, trigger star births, and enrich galaxies with the elements needed for planets and life. With JWST as our guide, we're finally seeing these processes unfold in real time, uncovering a universe far more dynamic and interconnected than we ever imagined. Among all the hypergiants in our cosmic neighborhood, none captivates astronomers quite like Betelgeuse, the fiery shoulder of Orion and one of the brightest stars in our night sky. This red supergiant, just 650 light-years away, is so colossal that if it replaced our Sun, its outer layers would stretch beyond the orbit of Mars. But what really makes Betelgeuse extraordinary isn't just its size. It's the star's bizarre, unpredictable behavior. In late 2019, Betelgeuse began dimming dramatically, losing 2/3 of its brightness in mere months. For a star normally visible even in light-polluted cities, this sudden fade sparked global speculation. Was this the prelude to a supernova or something even stranger? The truth turned out to be both simpler and more fascinating. Observations from the Hubble Space Telescope revealed the dimming wasn't caused by internal collapse, at least not yet, but by a colossal stellar sneeze. Betelgeuse had ejected a massive cloud of superheated gas, which cooled into dust as it expanded, temporarily obscuring our view. Imagine a volcano spewing ash high enough to blanket half a continent. That's the scale of this eruption, except with stellar material moving at 200,000 miles per hour. The event left astronomers stunned, proving even well-studied stars can still surprise us. Yet the real question lingers: how close is Betelgeuse to its inevitable demise? Unlike distant hypergiants, this star is near enough that its death will be a once-in-human history spectacle. When it finally explodes, the supernova could shine as brightly as a full moon for weeks, casting shadows at night and remaining visible in broad daylight. The last time humans witnessed such an event was in 1604, when Kepler's supernova appeared in our skies, but Betelgeuse's detonation would be 30 times closer and far more spectacular. What makes Betelgeuse a prime supernova candidate is its advanced state of decay. Spectral analysis shows it's already burning silicon in its core, the final element a star can fuse before catastrophic collapse. Unlike longer-lived stars, Betelgeuse has exhausted 90% of its nuclear fuel, leaving it teetering on the edge. The countdown could last millennia or end tomorrow. There's no way to predict the exact moment gravity will overwhelm the star's last defenses. For scientists, Betelgeuse offers an unprecedented opportunity. Its proximity allows telescopes to study surface details normally impossible to see on distant stars, like the vast convective cells that bubble material across its face, each larger than Earth's orbit. These observations refine our models of stellar evolution, helping decode the final chapters of hypergiant lives. Every flicker, every dimming event is a clue written in starlight, a cosmic Rosetta Stone for understanding how the universe's mightiest stars meet their explosive ends. What's certain is this: when Betelgeuse does go supernova, it won't just be an astronomical event, it'll be a human one. Cultures worldwide will witness the same celestial drama, united under a temporarily rearranged night sky. The explosion itself poses no danger. 650 light-years is a safe distance, but its light will carry reminders of our universe's impermanence. The same Orion constellation that guided ancient navigators will change forever, losing one of its brightest jewels. Yet in that loss lies a deeper truth: stars die so new ones can rise. The iron in our blood, the calcium in our bones, these elements were born in explosions like Betelgeuse's future demise. Its death, however spectacular, is just another step in the cosmic cycle that makes our existence possible. Deep within the heart of a hypergiant star, an entirely different kind of symphony plays out, one where the instruments are shockwaves and the musicians are the laws of physics themselves. These cosmic behemoths don't just sit quietly burning fuel, they resonate like colossal bells, their interiors pulsing with vibrations so powerful they distort the star's entire shape. Astronomers call these phenomena starquakes, and they're not just fascinating to study, they're our only window into the hidden structures of these distant giants. The process begins in the star's seething core, where nuclear fusion generates unimaginable pressures. Occasionally, pockets of overheated gas erupt, sending pressure waves racing outward through the star's layers at speeds exceeding hundreds of thousands of miles per hour. Picture dropping a boulder into a lake, except the lake is a raging plasma ocean, and the ripples are supersonic tsunamis that take weeks to cross the star's diameter. These waves bounce between the star's surface and core, creating standing waves that make the entire star rhythmically expand and contract, sometimes by millions of miles. What's remarkable is how these pulsations betray the star's secrets. Just as geologists use earthquakes to map Earth's interior, astronomers analyze starquakes to peer inside stars they'll never physically reach. By measuring minute changes in a hypergiant's brightness, often as little as 1%, scientists can decode the frequencies of these vibrations, revealing the star's density, composition, and even the existence of hidden layers. For instance, unusually slow pulsations in Betelgeuse suggest it has a vast convective zone near its surface, where plasma bubbles like water in a boiling pot. Some hypergiants take this behavior to extremes. Stars like Eta Carinae exhibit strange modes, where vibrations don't follow predictable patterns, hinting at internal structures defying current models. Others, like Rho Cassiopeiae, pulse so violently they eject entire solar masses of material in rhythmic outbursts. The most extreme cases, such as the yellow hypergiant HR 8751, display overlapping waves that interfere with one another, creating chaotic brightness fluctuations once mistaken for approaching supernova. Technology has revolutionized this field. Space telescopes like Kepler and TESS detect starquakes by capturing minuscule brightness dips lasting hours or days, while ground-based spectrographs track surface movements through Doppler shifts. Combined, these tools let scientists build 3D models of stellar interiors, uncovering features like rotating cores or magnetic fields twisting beneath the surface. Perhaps the most startling revelation is how these vibrations influence a hypergiant's fate. Persistent pulsations can weaken a star's gravitational grip on its outer layers, priming it for catastrophic eruptions. In rare cases, resonant waves might even trigger premature collapse, like a singer shattering glass with the right note. Every ripple tells a story of a star's past, its present turmoil, and the spectacular explosion awaiting it in the future. And with each new observation, we're learning to listen. Yellow hypergiants are the universe's ultimate shape-shifters, stars that defy the usual stellar classifications by violently oscillating between extreme states. Among these celestial chameleons, Rho Cassiopeiae stands out as both a marvel and a mystery. Imagine a star so unstable that its surface temperature can swing from a searing 12,000 degrees down to a cool 5,000 degrees in mere months, switching from blue-white to deep red like a cosmic mood ring. These aren't subtle changes, they're full-scale identity crises where the star tears itself apart and rebuilds in real time. What drives this wild behavior is a battle between two forces. Normally, massive stars evolve steadily from hot blue supergiants to cooler red hypergiants as they age. But yellow hypergiants like Rho Cassiopeiae get stuck in the transition, trapped in a feedback loop where their outer layers puff up and collapse unpredictably. Radiation pressure fights gravity, neither winning for long, creating a star that's essentially gasping for equilibrium. The result, eruptions where the star sheds entire Earth masses of material in violent outbursts like a volcano constantly on the verge of explosion. The most dramatic event in VY Cassiopeia's history occurred in 2000, when it ejected nearly 10,000 times the mass of Earth in a single episode. For weeks, it became one of the brightest stars in the Milky Way, its expelled gas forming an expanding shell visible to telescopes. Unlike the steady stellar winds of most hypergiants, these eruptions are chaotic, more like stellar tantrums than predictable processes. Spectroscopic analysis revealed something even stranger. The ejected material contained molecules like titanium oxide, normally found in much cooler stars. It was as if the star's outer layers had briefly impersonated a red giant before reheating. What makes these stars so valuable to astronomers is their rarity. Scientists estimate there are fewer than 20 known yellow hypergiants in our galaxy, making each one a precious laboratory for extreme physics. Their transitional nature offers glimpses into how massive stars evolve or fail to. Some, like IRC plus 10420, even develop circumstellar disks resembling those of newborn stars, proving that death and birth in the cosmos are often two phases of the same cycle. Yet for all their fury, yellow hypergiants are cosmic dead ends. Stars like VY Cassiopeiae won't live to see old age. They're destined for spectacular collapses, likely within the next 50,000 years. Every eruption brings them closer to the edge, shedding mass until their cores can no longer sustain fusion. When that happens, their deaths will be anything but quiet, either as supernova bright enough to outshine their host galaxies or as rarer pair instability explosions that leave nothing behind. Until then, they'll keep dancing between states, reminding us that even the mightiest stars are never truly stable. A Betelgeuse supernova wouldn't just be a light show. It would unleash a wave of energy capable of reshaping Earth's atmospheric chemistry. At 650 light-years away, this dying star is close enough to deliver a cosmic gut punch without obliterating our planet, the first sign we'd notice. A surge of ultraviolet and X-ray radiation hitting our upper atmosphere within seconds of the explosion, ionizing atoms and triggering cascades of chemical reactions. Satellite communications could falter as the ionosphere becomes turbulent, while GPS signals might bounce unpredictably for weeks, throwing off navigation systems worldwide. But the real threat comes days later when the slower-moving debris arrives. High-energy protons and heavier atomic nuclei, particles accelerated to nearly light speed, would bombard Earth like microscopic bullets. Astronomers call this a cosmic ray spike, and its effects could be devastating. Our planet's magnetic field would funnel these particles toward the poles, creating auroras so bright they'd be visible at midday, while also generating electrical currents strong enough to overload power grids. The last time Earth experienced a similar event, in 1859, the Carrington event telegraph systems caught fire and operators received electric shocks. A Betelgeuse supernova could unleash a storm 10 times more powerful, potentially frying transformers and plunging continents into darkness for months. The atmosphere itself wouldn't escape unscathed. The deluge of radiation would split nitrogen and oxygen molecules, creating nitric oxide compounds that attack the ozone layer. Simulations suggest up to 30% of our protective ozone could vanish within weeks, exposing ecosystems to DNA-damaging UV radiation for years. Phytoplankton, the base of the ocean food chain, might suffer mass die-offs while land plants could show stunted growth. Humanity would face rising skin cancer rates and crop failures until the ozone slowly repaired itself. Yet there's an ironic twist to this devastation. The same explosion threatening our technology would also deliver rare isotopes like iron-60, a radioactive tracer only produced in supernova. Scientists have already found traces of it in Antarctic ice and deep-sea sediments, evidence of past stellar explosions that showered Earth with stardust. In a sense, we're the products of ancient hypergiant deaths, our very atoms forged in catastrophes like Betelgeuse's impending demise. So while we brace for potential disruption, we should also remember, this star's death throes will one day seed new worlds, just as others once seeded ours. Before the first galaxies, before planets, before even ordinary stars could form, the universe hosted a breed of giants so colossal they make today's hypergiants look like faint candles. These were population 3 stars, the universe's firstborn, forged from pure hydrogen and helium in the cosmic dawn. Unlike modern stars, which form from gas enriched by previous stellar generations, these primordial titans had no heavy elements to help them cool and fragment. The result, stars that may have reached staggering masses 1,000 times heavier than our Sun, burning with the brilliance of small galaxies. Their formation was a cosmic anomaly. In today's universe, gas clouds splinter into many smaller stars as dust and metals radiate away heat. But in those early eons, without these cooling agents, gas remained hot and diffuse, collapsing into single, monstrous stars instead of clusters. Picture a nebula not giving birth to a stellar nursery, but to a solitary, unimaginably vast inferno, one so bright its ultraviolet radiation could have reionized the entire cosmos, stripping electrons from atoms across vast distances. These stars didn't just burn differently, they died differently too. With no metals to stabilize their cores, they consumed their nuclear fuel at breakneck speeds, lasting mere millions of years before collapsing. Their deaths weren't normal supernovas, but hypernovas' explosions so violent they might have unleashed gamma-ray bursts strong enough to sterilize entire swaths of the early universe. The energy released would have been mind-bending, outshining all the stars in a modern galaxy combined. Yet this destruction was also creation. The explosions of population 3 stars scattered the first heavy elements carbon, oxygen, silicon, into the void, transforming pristine gas into the enriched raw materials needed for future stars and planets. Every iron atom in your blood, every calcium molecule in your bones, traces its lineage back to these cataclysmic deaths. Without them, the universe would have remained a featureless sea of hydrogen, incapable of forming rocky worlds or life. The irony, we've never directly observed a population 3 star. They existed so early, within a few 100 million years of the Big Bang, that even our most powerful telescopes struggle to glimpse their light, now redshifted into near invisibility. Yet their fingerprints are everywhere. The metal-poor stars in our galaxy's halo, the chemical gradients in ancient gas clouds, all whisper of these long-vanished giants. Some theorists even suggest their remnants, black holes from those first collapses, might now lurk at the centers of galaxies, grown into the supermassive behemoths we call quasars. So while we marvel at today's hypergiants, remember, they're just the descendants of a lost generation, a breed of stars so wild and massive they could only exist in a universe still learning the rules. Their brief, brilliant lives set the stage for everything that followed, proving that even in cosmic history, the most pivotal chapters are often written by those who burn brightest and vanish fastest. Some stars don't just burn brightly, they flee across the galaxy like cosmic fugitives, hurtling through space at speeds that defy imagination. Zeta Ophiuchi is one such runaway, a blue hypergiant racing through interstellar space at nearly 67,000 miles per hour, fast enough to cross the distance from Earth to the Moon in just 6 hours. Behind it stretches a colossal bowshock, a glowing arc of compressed gas 14 light-years wide, like the wake of a ship plowing through the cosmos. But this star wasn't born in motion, it was violently ejected, catapulted by forces powerful enough to send a stellar titan careening through the galaxy. The culprit, a cosmic slingshot from a supernova explosion in a binary system. Here's how it works. When two massive stars orbit each other and one explodes, the sudden loss of mass releases its companion like a snapped tetherball. The surviving star, no longer held in balance by gravity, gets flung outward at incredible speeds, carrying the momentum of its dead partner's detonation. For Zeta Ophiuchi, this likely happened when its former sibling, a star even more massive than itself, collapsed in a cataclysmic supernova. The shockwave didn't just send Zeta Ophiuchi flying, it stripped away much of its outer layers, exposing searing hot inner regions that now blast surrounding space with ultraviolet radiation, lighting up the interstellar medium like a flare in the dark. What's fascinating is how these runaway stars transform their surroundings. Zeta Ophiuchi's bow shock isn't just a visual spectacle, it's a laboratory for extreme physics. The shock front heats interstellar gas to millions of degrees, creating conditions typically found near supernova remnants. Molecules that would normally stay dormant get smashed apart and reassembled, triggering chemical reactions that shouldn't occur in the quiet depths of space. Some astronomers speculate these turbulent zones might even seed the formation of complex organic compounds, the precursors to life, as the star's radiation cooks the raw materials floating between the stars. But Zeta Ophiuchi isn't alone in its exile. Other hypergiants like Ae Aurigui and Mu Columbi streak through the galaxy with similar histories, their trajectories tracing back to the same stellar nursery in the Orion Nebula. Like shrapnel from an ancient explosion, these runaway stars map the violent events that shaped them, their paths telling stories of binary systems torn apart by death. Some may eventually escape the Milky Way entirely, becoming intergalactic voyagers destined to drift forever in the void between galaxies. Yet for all their solitude, runaway stars serve a purpose. As they barrel through interstellar clouds, their powerful winds and radiation compress surrounding gas, potentially triggering the birth of new stars in their wake. They're cosmic nomads, destroyers and creators in one, leaving behind trails of chaos and possibility. So the next time you gaze at the night sky, remember, some of those steady lights are anything but stationary. They're stellar outlaws flung across the cosmos by forces beyond comprehension, writing their stories in light and motion across the canvas of space. At first glance, the color of a star seems straightforward. Blue means hot, red means cool, right, but nature loves breaking rules, and hypergiants are no exception. Some of the universe's most scorching stars appear deep red, while others blaze unmistakably blue, creating a cosmic illusion that challenges everything we think we know about stellar temperatures. The secret lies not in the stars themselves, but in what surrounds them and the violent lives they lead. Take the red hypergiant VY Canis Majoris. Its surface temperature exceeds 3,000 degrees, far hotter than a blast furnace, yet it glows like a dying ember. The reason? A cocoon of its own making. As the star sheds colossal amounts of material, ejected gas condenses into dust grains that act like a cosmic fog machine, scattering shorter blue wavelengths while letting longer red light pass through. It's the same reason sunsets on Earth appear red, except here the star is wrapped in its own permanent twilight. Now contrast that with a blue monster like Eta Carini. At 40,000 degrees, its surface could vaporize steel, and its color matches that ferocity. Unlike red hypergiants, Eta Carini's violent winds sweep away surrounding dust, leaving its raw ultraviolet fury exposed. But there's a twist: this star wasn't always blue. Centuries ago, it likely appeared red during its great eruption, when ejected material temporarily reddened its glow. Today, stripped of that shroud, it's a blistering sapphire in the cosmic dark. The color paradox deepens when we consider circumstellar disks. Some hypergiants, like IRC plus 10420, are sandwiched between extremes: blue-white at the poles where hot gas escapes freely, but red at the equator where a thick disk of dust dims their brilliance. Viewed from different angles, these stars could be mistaken for two entirely separate objects. Even more bizarre are stars like Rho Cassiopeiae, which unpredictably switch between yellow and red as they puff off layers in violent outbursts. What's truly fascinating is how these colors deceive even seasoned astronomers. Early observations of the Pistol star pegged it as relatively cool until infrared telescopes revealed its true nature, a blue hypergiant masquerading as a red one, its light filtered through 30 light-years of intervening dust. Similarly, Westerlund 126's apparent redness hides a star so luminous it outshines entire star clusters. The takeaway: a star's color isn't just about temperature, it's a complex interplay of physics, environment, and perspective. These cosmic chameleons remind us that reality often wears disguises, and the universe's most spectacular deceptions happen when starlight dances with dust. Hidden beneath the turbulent surfaces of hypergiant stars, another invisible force shapes their destiny: magnetic fields of unimaginable power. Take HD 45166, a Wolf-Rayet star with a magnetic field 100,000 times stronger than Earth. This isn't just a background feature, it's a cosmic puppeteer, twisting stellar winds into spirals and triggering eruptions that defy conventional physics. Unlike the relatively orderly outflow from our Sun, this star's winds whip outward in chaotic jets, constrained by magnetic loops that act like celestial railroad tracks for superheated plasma. The mechanics at play here are both elegant and violent. As charged particles in the star's atmosphere interact with these intense fields, they get funneled along magnetic lines, accelerating to speeds surpassing 6 million miles per hour. Picture a garden hose with water flowing smoothly, then suddenly kinking it, creating high-pressure sprays in unpredictable directions. That's essentially what happens when magnetic fields sculpt stellar winds, except the hose is the size of our solar system, and the water is plasma hot enough to vaporize diamonds. These magnetic forces don't just direct winds, they amplify eruptions. When magnetic loops become too twisted, they snap like overstretched rubber bands, releasing energy equivalent to billions of atomic bombs. HD 45166's most powerful recorded outburst flung a chunk of its atmosphere into space at 10% light speed. A mass the size of Mars hurled so violently it left a glowing trail detectable for light years. Some astronomers compare this to solar flares, but that's like equating a campfire to a volcanic explosion. What's truly fascinating is how these magnetic fields originate. Unlike Earth's relatively stable dipole field, hypergiants generate magnetism through turbulent interior dynamos where plasma currents twist and shear at incomprehensible scales. Simulations suggest some of these fields might be fossilized, trapped remnants from the star's formation, compressed and amplified as the star evolved. Others could emerge from differential rotation, where the star's equator spins faster than its poles, creating magnetic instabilities like a cosmic version of swirling water in a drain. The implications extend far beyond single stars. Magnetic hypergiants act as cosmic particle accelerators, their fields launching high-energy cosmic rays that pepper interstellar space. Some theories even suggest these fields could influence how hypergiants eventually collapse, potentially explaining why some supernovae show bizarre asymmetrical explosions as trapped magnetic energy finally breaks free. Every twisted magnetic line, every sudden eruption, is a clue to understanding how the universe's most powerful stars live, die, and shape the cosmos around them. HD 45166 isn't just a curiosity, it's a preview. As telescopes grow more sophisticated, we're finding similar magnetic monsters across the galaxy, each adding pieces to a puzzle we're only beginning to assemble. Their existence proves that in the hearts of these titans, magnetism isn't just a side effect. It's a defining force as crucial to their story as gravity or nuclear fusion. And that story, written in arcs of plasma and bursts of radiation, is still being decoded one magnetic field measurement at a time. even the universe's mightiest hypergiants pale in comparison to a theoretical class of monsters that may have existed in the cosmic dawn quasi-stars, black hole-powered behemoths so vast they could have dwarfed entire solar systems. Picture a star not hundreds but thousands of times more massive than our Sun, with a newborn black hole simmering at its core like a demonic engine. These hypothetical leviathans would have formed when the first clouds of pristine hydrogen collapsed into supermassive protostars so dense that their cores ignited black holes before fusion could even stabilize them. Unlike modern stars where fusion fights gravity's crush, quasi-stars would have balanced on a razor's edge. The central black hole, perhaps a few solar masses wide, would devour matter from the star's inner layers, releasing torrents of radiation that pushed outward against the collapsing weight of the outer envelope. It's a cosmic paradox, a black hole's appetite sustaining the very structure containing it. The energy output would be unimaginable equivalent to a small galaxy's worth of starlight streaming from a single object. The life cycle of these entities reads like something from mythology. Fed by the surrounding gas, the central black hole could grow to thousands of solar masses within a few million years, seeding the supermassive black holes we now find at galactic centers. Eventually, when the star exhausted its fuel, the black hole would emerge like a phoenix from the ashes, free to grow further by consuming nearby matter. Some theories even suggest these objects could explain the existence of early supermassive black holes puzzles that defy conventional formation timelines. What's chilling is how different quasi-stars would have looked from modern hypergiants. Their surfaces, cooled by sheer size, might have resembled red supergiants, but their cores would have blazed with X-rays from the black hole's accretion disk, painting the surrounding gas with eerie, shifting patterns. Stellar winds wouldn't just be streams of particles, but geysers of plasma ejected by magnetic fields twisting near the event horizon. Yet for all their grandeur, quasi-stars were likely doomed by their own success. As the universe aged, supernova enriched gas clouds with metals, allowing stars to form smaller and more efficiently. The conditions for these black hole-cored giants vanished forever, leaving only their descendants, supermassive black holes, as clues to their existence. Their story reminds us that the early universe operated by different rules. Where physics stretched to extremes, we can now only simulate in supercomputers or glimpse in the distant light of quasars. A realm where stars weren't just big but unimaginable. At the heart of the Tarantula Nebula, a chaotic stellar nursery in the Large Magellanic Cloud, lies one of the universe's most extreme laboratories, the R136 cluster. This cosmic furnace crams hundreds of scorching young stars into a space barely larger than our solar system, creating conditions so dense and violent that the laws of stellar physics seem to bend. Here, in this maelstrom of radiation and gravity, stars don't just form. They collide, merge, and rewrite the rulebook on how massive a star can truly become. The cluster's crown jewel, R13601, defies everything we thought we knew about stellar upper limits. Weighing in at over 250 solar masses, this blue hypergiant shouldn't exist, at least not according to traditional models. The Eddington limit, a cornerstone of astrophysics, suggests stars beyond 150 solar masses should tear themselves apart with their own radiation pressure. Yet R13601 burns with the fury of nearly 9 million suns, its existence a tantalizing clue that in the universe's most extreme environments, stars cheat. How does this cosmic loophole work? The answer lies in the cluster's frenzied density. Imagine a room where stars are packed so tightly that their gravitational pull constantly tugs at one another. Close encounters become inevitable. Over time, these interactions can slingshot stars into collision courses, their mutual gravity overcoming electrostatic repulsion as they spiral together. When two massive stars merge, their combined mass doesn't just add up, it enters uncharted territory. Computer simulations suggest these mergers can momentarily create objects exceeding 300 solar masses, though they quickly shed excess weight through apocalyptic stellar winds. But collisions aren't the only path to impossible stars. Some theorists propose a darker mechanism, stellar vampirism in overcrowded systems. Picture a massive protostar surrounded by smaller siblings in a gravitational dance. As they jostle for position, the largest star can strip material from its neighbors, gorging itself like a cosmic kingpin. In R136's free-for-all environment, this theft might happen repeatedly, allowing one star to amass unheard-of proportions while others wither. The cluster's intense radiation field adds another twist. Normally, a forming star's light pressure pushes away nearby gas, limiting growth. But in R136, the collective ultraviolet glare from surrounding stars ionizes this gas, turning it into plasma that resists being blown away. This trapped material becomes an all-you-can-eat buffet for developing hypergiants, fueling runaway growth. It's the astrophysical equivalent of a windstorm so strong it pins leaves against a fence, except here, the leaves are solar masses of gas and the fence is a star's gravitational pull. What's perhaps most astonishing is how temporary these monsters are. Stars like R13601 live fast and die young, their titanic fusion rates burning through fuel in just 2 million years, a cosmic heartbeat. Their deaths are equally extreme, likely collapsing directly into black holes without supernova, or exploding as pair instability events that vaporize them completely. Yet in their brief lives, they reshape their surroundings, their radiation sculpting nearby gas clouds and triggering new rounds of star formation. The R136 cluster forces us to reconsider our definitions of impossible. In the quiet suburbs of the galaxy where stars form in isolation, limits hold firm. But in these urban centers of stellar activity, chaos breeds exceptions. And those exceptions may hold the key to understanding how the universe's first, most massive stars came to be. Every telescope trained on this region peels back another layer, revealing a cosmos far more inventive than our textbooks ever suggested. The next revolution in our understanding of hypergiant stars is already taking shape not in the depths of space, but in the deserts of Chile, where engineers are assembling a telescope so powerful it could make Betelgeuse's surface features as clear as craters on the moon. The Extremely Large Telescope, or ELT, represents a quantum leap in observational capability, with a 39-meter primary mirror that will gather more light than all of history's major telescopes combined. When it achieves first light in 2028, this behemoth won't just observe stars, it will dissect them, resolving details as small as 5 milliarcseconds across. For a star like Betelgeuse that translates to surface features spanning just 30 million miles cosmic geography on a scale we've never seen. What makes the ELT extraordinary isn't just its size, but its adaptive optics system, a technological marvel that corrects atmospheric distortion 1,000 times per second. Current telescopes glimpse hypergiants as blurry orbs, but the ELT's images will reveal convective cells, magnetic storms, and mass ejections in real time. Imagine watching Betelgeuse's great dimming event unfold with HD clarity, seeing plumes of gas swell from its surface like solar prominences on steroids. Or tracking VY Canis Majoris' eruptions as they happen, mapping how stellar winds accelerate from a few thousand to millions of miles per hour. But resolving surfaces is just the beginning. The ELT spectrographs will analyze hypergiant atmospheres atom by atom, detecting rare isotopes expelled during eruptions and measuring Doppler shifts in gas clouds with unprecedented precision. This could finally answer why some hypergiants shed mass in violent bursts while others peel away steadily like cosmic onions. The telescope's mid-infrared instruments will peer through dust shrouds around stars like Westerlund 126, uncovering hidden companions or accretion disks that current tools miss. Nor is the ELT alone in this new era. NASA's Nancy Grace Roman Space Telescope, launching around 2027, will survey hypergiants across the Milky Way with a field of view 100 times wider than Hubble's, perfect for catching rare events like yellow hypergiant transitions or pre-supernova outbursts. Meanwhile, the Square Kilometre Array Radio Telescope network will map hypergiant magnetic fields in 3 dimensions, revealing how their colossal loops channel stellar winds into space. These instruments arrive just in time. Betelgeuse's recent antics proved we're witnessing hypergiant evolution on human timescales. With tools like the ELT, we won't just be passive observers. We'll have front-row seats to stellar metamorphosis, watching as these titans rewrite their destinies before our eyes. The data could redefine everything from supernova prediction models to theories about how the first stars formed. After centuries of squinting at blurry dots, we're finally getting the microscope the universe's biggest stars deserve. What we discover may be stranger than fiction, perhaps pulsations preceding eruptions that hint at imminent collapse, or asymmetrical surfaces revealing hidden black holes forming within. One thing's certain, the golden age of hypergiant astronomy hasn't even begun. When these telescopes open their eyes, the cosmos won't just share its secrets, it'll hand us the entire playbook. In the violent heart of dense star clusters, gravity occasionally orchestrates a spectacle so extreme it defies belief: hypergiant stars colliding in slow-motion cosmic car crashes. Picture 2 stellar behemoths, each hundreds of times more massive than our Sun, locked in a death spiral by mutual gravitational attraction. As they inch closer over millennia, their outer atmospheres begin to mingle, creating swirling bridges of superheated plasma. When their cores finally merge, the energy released would make even supernova seem tame, a temporary supermassive star, igniting with the brilliance of 100 million suns. These apocalyptic mergers aren't just theoretical. In clusters like R136, where stars are packed tighter than atoms in solid metal, close encounters are inevitable. Computer simulations show that when 2 hypergiants collide, the resulting object can briefly exceed 400 solar masses, a weight class so extreme it triggers exotic nuclear reactions never seen in normal stars. For a fleeting moment, this Frankenstein's monster of a star burns elements like magnesium and neon directly in its core, skipping the usual fusion sequence in a desperate bid to stabilize. The aftermath depends on precise conditions. Lower mass mergers might produce a single, unstable hypergiant that quickly sheds excess weight through violent stellar winds. Imagine a star vomiting its own outer layers into space at millions of miles per hour. More extreme collisions could trigger immediate pair instability, where the combined core becomes so hot that matter and antimatter particle pairs spontaneously form, leading to a total thermonuclear detonation. There's even speculation about quasi-star scenarios, where the merged object's core collapses into a black hole while still encased in an enormous gas envelope, a celestial matryoshka doll with a dark heart powering its outer brilliance. What makes these events truly transformative is their role in seeding the universe with rare elements. The unique pressures and temperatures during hypergiant mergers can forge exotic isotopes like gold, platinum, and uranium far more efficiently than ordinary supernova. Some astronomers suggest that the precious metals in Earth's crust might trace their origins to such cataclysms billions of years ago, when the Milky Way star clusters were denser and collisions more frequent. Yet witnessing one remains the holy grail of stellar astronomy. The best candidates lie in extreme environments like the Arches cluster near our galaxy's center, where stars orbit so closely that collisions may occur every few thousand years, a blink in cosmic time. Future telescopes like the ELT could catch the infrared afterglow of such an event, while gravitational wave detectors might sense the ripples in spacetime as the star's cores finally coalesce. Until then, these titanic mergers exist at the intersection of mathematics and imagination, reminders that in the universe's most crowded neighborhoods, even stars can't escape each other's pull. From their unimaginable scale to their explosive deaths, massive stars rewrite the rules of physics at every turn. We've witnessed hypergiants like VY Scuti, so vast they could swallow our solar system whole, and daredevils like the pistol star blazing through space at breakneck speeds. We've explored stellar vampires siphoning life from their companions, and cosmic time bombs like Eta Carini teetering on the edge of annihilation. These titans don't just burn, they sculpt the universe, forging heavy elements in their cores and scattering them across galaxies in supernovae that outshine entire star clusters. Their collisions birth new celestial monsters, their magnetic fields twist space itself, and their deaths seed the cosmos with the building blocks of planets and life. Yet every answer uncovers new mysteries. Why do some hypergiants defy the Eddington limit? What triggers the erratic tantrums of luminous blue variables? Could quasi-stars, black hole-powered behemoths from the dawn of time still lurk in the cosmic shadows? The more we learn, the clearer it becomes. Massive stars are the universe's ultimate paradoxes. They live fast and die young, yet their legacy spans billions of years. They're rare, yet their influence is everywhere, in the iron in our blood, the calcium in our bones, even the gold in our jewelry. As telescopes like the ELT and JWST peel back the cosmic veil, we stand on the brink of revelations that could rewrite astronomy itself. Perhaps we'll catch a hypergiant mid-collision or decode the final warning signs of an impending supernova. Maybe we'll even glimpse population 3 stars, the lost giants of the cosmic dawn. One thing's certain, the universe's grandest spectacles are still unfolding, hidden in plain sight. So the next time you gaze at the night sky, remember those tiny pinpricks of light harbor forces beyond imagination. Behind their twinkle lies a story of creation and destruction, of chaos and beauty, written in the life and death of stars too massive to comprehend. The cosmos has shown us 30 wonders today, but how many more await discovery? The greatest chapters of stellar physics may still be unwritten, waiting for curious minds to turn their eyes and telescopes skyward.